Okay guys, 3.5 exponential and logarithmic models. We're going to recognize 5 most common types of models involving exponential and logarithmic functions. We're going to use the exponential growth and decay functions to model and solve real-life problems. Use the Gaussian functions to model and solve real-life problems. Use logistic growth functions to model and solve real-life problems. And use logarithmic functions to do the same thing. So the 5 most common types of mathematical models involving exponential functions and logarithmic functions are listed below. And these are the ones that we're going to be using. And so one of the things that that you might want to notice, okay, my pen is not working. Oh well, is, let me get the highlighter. So these are the functions that we're talking about, these here. And then if you'll notice, they already have them graphed for you. So let's go to the next level. So we're looking at this first one here, and it says online advertising. So the sad thing, which they do this all the time, is they have given you the function already. So they've given you the equation, which I wish they wouldn't. I wish they would let us do it ourselves. So with this, what we want to do is we want to use that equation to solve algebraically. So t represents the year, with t equals 10 is 2010. So then of course this one would be 11, this would be 12, this would be 13, and this would be 14. For the model. So according to this model, in what year will the amount spent on mobile online advertising be approximately 65 billion? So what we want to do is we want to find out 65 billion. So what we want to say, and I don't know why my pen isn't working, is 65 is equal to 0.00036 e to the 0.7563 t. So the first thing you do is you try to get your, let me make this a little bit bigger. Okay, you're going to try to get your function, your e, alone. So what we need to do is we need to divide here. So then what we want to do is we want to try to get t by itself. So we're trying to get this. So what we're going to do is we're going to natural log. So if we natural log 65 over 0.00036 is equal to, and then natural log e to the 0.7563 t, what happens is we can bring that down. This can come down here. And we know that the natural log of e is 1. So now we've got the natural log of 65 over 0.00036 is equal to 0.7563 t, and then divide by that and plug all of that into the calculator, and you'll find out that t is equal to 16 years. Now, of course, we can go through and we can graph it on this graph right here, and then look to find out for t, when is t 60, or when is t 65, and then you've got your answer. Okay, so this next one is we need to think about what we have, and so we've got y is equal to, let me make this a big screen because I need a lot of space. Y is equal to 100 when t equals 2, and then y equals, hold on, okay, y equals 300 when t equals 4. So we're going to set it up using our equation. So we have two equations going on here. We've got 100 is equal to A, E, 2B, and then we've got 300 is equal to A, E, 4B. What we need to do is we need to figure out what is B. So what I can do is just solve for A for one of these. So I'm just going to divide by E2B on both sides. And then I'm going to plug it into my other equation. So I have 300 is equal to, we just solved for A, which is 100 over E2B, e to the 4B. So you need to think about that. These are going to cancel out, which is going to leave us with 300 equals 100 E2B. I divide by 100. I'm trying to get E by itself. So I've got 3 is equal to E2B. I want to bring the B down, so natural log both sides. And I end up with natural log of E is 1, and so I'm going to bring the 2B down here. So I've got the natural log of 3 is equal to 2B. Therefore, B is equal to the natural log of 3 divided by 2. Okay, so I'm going to go back into my function, and I'm going to replace this stuff. So I solved for A. I'm trying to remember, where did I solve for? I guess I didn't. Okay, so let's solve for A. So let me get a different color just so you can see it. Okay, so A, I'm going to go ahead and let's just solve this one here for A. So we know that A is equal to 100 over E to B. And we know B is a natural log of 3 over 2. So A is equal to 100 over E2 times the natural log of 3 over 2. So we know A is equal to E to the natural log of 3. So when I solve that, I find out that A is equal to approximately 33.33. So with that, we can go back to our equation. So I'm going to change my color. And we can say that Y is equal to, because we solved for A, 33.33. E, and then we solved for B, and so B is 0.0549. T. So we want to know after 5 days, that was what our original answer was, after 5 days, how many flies? So we're just going to plug that in. 33.33 E 0.549 times 5. And what you get is approximately 520 flies. Okay, let's go to example 3. Okay, so example 3, it says estimate the age of a newly discovered fossil for which the ratio of carbon-14 to carbon-12 is so-and-so. So before this, we were given that the formula for the carbon-12 is 1 over 10 to the 12th e to the negative t over 8,223. This is a formula that was given to us. So using that, what we're going to do is we are going to plug in our r. So we've got 1 over 10 to the 13th equals 1 over 10 to the 12th e to the negative t over 8,223. So what you do then is we want to try to get e to the negative t8. We want to get that all by itself. So to get that by itself, we just have to multiply by 10 to the 12th. So if I go 10 to the 12th over 10 to the 13th is equal to e to the negative t, 8,223, right? Which means these are going to cancel out and leave us with just 1 over 10. Now what I want to do is I want to natural log both sides. So natural log of 1 over 10 is equal to, and then when I natural log e, that means I can bring this down. So negative t over 8,223. And the natural log of e is 1. So that pretty much cancels that out. So what I've got now is I'm just going to go ahead and multiply by, so 8,223 times the natural log of 1 over 10, and then I'm going to do the negative because I want t to be positive, and that will give me t. So therefore, t equals 18,934. So to the nearest thousandth year, the age of the fossil is about 19,000 years. Now, of course, for the graphical sense, what we can do is graph two graphs. We can do 1 over 10 to the 12th e to the negative x over 8,223, and then our second graph would be 1 over 10 to the 13th. And what you want to do is you want to see where they intersect, and then that would solve that problem for you. Okay, this one is pretty straight up. All you have to do is you put this in your graphing calculator, okay, and what it's going to do is it's going to give you like a bell curve. So it's going to give you something that looks like this, and whatever this maximum is, that is your average score. So you're just going to go into your calculator and then look for the maximum value and then highlight it and see what that maximum is. All right, the next one we're going to talk about is logistic growth. That's what this formula is here. So let's move on to the next page. Okay, so on this next page, it says, on a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this equation, where y is the total number of students infected after t days. College will cancel class when 40% or more of the students are infected. How many of your students are infected in 5 days? Which means all you're going to do is you're going to take 5 and you're going to plug it into t. So apparently when they took it in, it was approximately, so this is y of 5, which means we plugged in 5. It was approximately 54 students. So that tells us how many after 5 days. After how many days will the college cancel classes? So what we need to know is, what is 40% of 5,000? Right? Because they said that they would cancel at 40%. Well, 40% of 5,000 is 2,000. So you want to know, according to this function, when will it be 4999 e to the negative 0.8 t. So what we want to know is, when is this, what time? So we're going to solve for t. So what we can do is we can just multiply by the denominator. Let me make this bigger so I got more space. So that means, and then we're going to divide by 2,000. So I'm going 1 plus 4 point, it's 4 point, right? Nope, it's not point. So 1 plus 4999 e to the negative 0.8 t times 2,000 is equal to 5,000. Divide by 2,000. So we've got 1 plus 4999e negative 0.8t is equal to 5 halves. Subtract 1. So now we got 4999e to the negative 0.8t is equal to, when you subtract 1, you get 3 halves. And then we want to divide by 4999. We're trying to get e by itself. So e to the negative 0.8t is equal to whatever that is. I don't know what that is. But it's 3 halves divided by 4999. To get that down, we natural log both sides. So now we've got negative 0.8t is equal to the natural log of 3 halves divided by 4999. And then finally, we're going to divide by negative 0.8. I'm going to put it in exactly like this in my calculator so that I end up with 10.14. And that's my final answer. For the graphing portion, just graph them. So y1 is going to be 5,000 over 1 plus 4999e to the negative 0.8x. y2 would be 2,000. And see where they intersect, and you get the exact same answer. Okay, so now we're looking at earthquakes, and so this is Richter scale. This is the magnitude that they do. So these are some examples of earthquakes, and we want to find out what find the intensity of each earthquake. So what we need to do is we need to take the magnitude. So you see that R is equal to 4.00. So our I sub 0, our initial amount is always 1. So we just replace it with 1. So we've got 4.0 equals the log of I over 1. So all I need to do is go this to the this equals this. So 10 to the 4.0 equals I. And so when we plug it in our calculator, that means the intensity is 10,000. Okay, now the next one is for Nepal. So let's, oops, I want to zoom in. Oops, hold on, let me zoom in. So this time I'm going to plug in 7.8 is equal to the log intensity over 1. So I'm going to go 10 to the 7.8 equals our intensity. And this time you get 63 million. So that's a lot, man. Holy smokes. The intensity of the earthquake in Nepal was about 6,300 times as great as that of the earthquake in Piedmont, California. All done.